Electricity and magnetism are interrelated and also interconvertible. For example, electric current passed through a conductor produces magnetic field which can be observed through a magnetic compass needle placed near the conductor. This proves that the moving electric charges produces magnetic field. However, a current is induced in a closed coil when subjected to a changing magnetic field. The phenomenon in which the electric current is generated by varying magnetic field is called electromagnetic induction. We will now discuss and learn about the experiments done by the Faraday and Henry relating to the electromagnetic induction. In the first experimental setup, a coil is connected to the galvanometer and north pole of the bar magnet facing towards the coil. When the bar magnet moves into the coil, then galvanometer needle shows deflection towards left side, indicating the presence of current in the coil. When the magnet is stationary, galvanometer shows zero deflection, indicates no current in the coil. When the bar magnet moves away from the coil, the galvanometer needle shows deflection towards right side, indicating the presence of current in the coil in opposite direction. When the magnet is stationary, galvanometer shows zero deflection, indicating no current in the coil. Let us see what happens if the south pole of the magnet faces the coil. When the magnet moves into the coil, then galvanometer needle shows deflection towards right side, showing the presence of current in the coil. When the magnet is stationary, galvanometer shows zero deflection, indicating no current in the coil. When the bar magnet moves away from the coil, then galvanometer needle shows deflection left side, showing the presence of current in the coil in opposite direction. When the magnet is stationary, galvanometer shows zero deflection, indicating no current in the coil. Thus, the galvanometer needle deflects only as long as the bar magnet is in motion. Once the bar magnet comes to rest, the galvanometer needle comes to the zero, indicating that no current in the coil. From these observations, we can conclude that even there is a relative motion between the bar magnet and the coil, an electric current is induced in the coil. When the speed of the bar magnet is more, the deflection produced in the galvanometer increases, which shows current induced in the coil is more. In second experimental setup, there are two coils. Coil 1 connected to the galvanometer and coil 2 connected to the battery. Due to the current in coil 2, a magnetic field is set up in coil 2 and this magnetic field is also associated to coil 1. When coil 2 is kept stationary and coil 1 is moved towards coil 2, a current is induced in coil 1 and a deflection is observed in the galvanometer to the left side of 0. When coil 1 is moved away from the coil 2, a deflection is observed in galvanometer to the right of 0. So, current is induced in the coil opposite directions. If coil 1 is kept stationary and coil 2 is moved towards coil 1, current is induced on coil 1 and a deflection is observed in galvanometer to the left of 0. If move coil 2 away from coil 1, a deflection is observed in the galvanometer to the right of 0. Hence, current is induced in the coil in opposite directions. From these all observations, we conclude that even there is a relative motion between these two coils, a current is induced in first coil. In third experimental setup, a tap key is provided in coil 2 circuit. When the key is closed, galvanometer shows a deflection towards left side, and when key is open, galvanometer shows a deflection towards right side. Here, galvanometer shows deflection only when the tap key is either closing or opening. This happens because of change in magnetic field during switching on or off. When we insert a ferromagnetic substance into the coil, it provides extra magnetic field and deflection in the galvanometer further increases. This shows increase in the current in the coil. Faraday's laws of electromagnetic induction. It gives the magnitude of induced EMF. From the observations of these three experiments, Faraday concluded that the rate of change of magnetic flux through a closed coil induces an EMF in it, and stated the law of electromagnetic induction. The magnitude of induced EMF in a circuit is equal to the rate of change of magnetic flux through the coil. When we put this law in the form of mathematical equation, induced EMF epsilon equals d phi by dt. When n number of turns are closely wound to form a coil, the EMF induced in each coil is same, and the total EMF induced in the coil is epsilon equals n d phi by dt. Here, total induced EMF can be increased by increasing the total number of turns of the coil.